Geothermal. Okay, last renewable energy source. Geothermal comes in two main flavors. One is home heating and cooling, which can be installed in pretty much any home, and then the other is electricity production, and that can only occur in very specific types of areas. I think I told you guys in an earlier video, when I moved into my house, we had an oil burning furnace. We had to pay for heating oil on a regular basis to come in. But after a couple of years, it broke down. So I was in a position where we absolutely had to replace our system. It was going to be thousands of dollars one way or the other. We don't have any natural gas line going to this neighborhood, so that was out. There was no option for that. So we were looking at either replacing the oil system or geothermal heating and cooling. We decided to go with geothermal heating and cooling, and it has been a great decision for us. The system was more expensive to put in, but at the time, this was 2015 or 2016, there were tax incentives to actually give us something like 20% of the cost back as rebates at the time. That incentive program for installing renewable energy sources in your home or other energy efficient options has since disappeared, but maybe it'll be reinstated. So our slide here says that geothermal heating and cooling can reduce costs by 70%. That depends on where you're coming from. Reduced by about 45%, I'd say, for us. But actually, if you consider that this year the cost of a barrel of oil has more than doubled from when we initially made the switch, then yeah, actually, maybe it has reduced our cost by 70% or more as a result of getting it. So, very efficient. How does it work? You see these pipes that are drilled underneath this house here. They snake up and down and up and down and up and down. So they run throughout the ground here. Let's say the air temperature spikes really high. It's 102 degrees outside. If you're to dig a hole down into the earth, even like a foot, right, that soil is still going to be pretty cool. If you go deep into the ground, it's going to remain around 50 degrees at all times. So the earth already is pretty cool, right? So why bother using electricity to try to cool off the house when you already have this nice reservoir of cold? Heat is a thing, cold's not really a thing. Cold is the absence of heat, but come with me on this. In order to try to cool your house off. So here's how the system works. A kind of antifreeze is pumped through these pipes, and any heat that's in the antifreeze gets lost to the ground around it because the earth stays around 50 degrees Fahrenheit all the time. And it comes back to the house much cooler than when it left. And then that antifreeze is, there's a heat exchanger where it absorbs excess heat from the house and then is sent back, now warmed up, through the pipes again until it cools off once more. So every time it follows this circuit, it's pulling a little bit more heat out of the house. And this is not entirely dissimilar to the way a normal air conditioner works either. It's just using the earth itself as a heat sink, effectively. Now, our house has two sets of these pipes running underneath it. It turns out it is way more energy efficient to just work a pump that is moving this antifreeze through these pipes than it is to work an air conditioner mechanism that is compressing and expanding Freon in order to try to pull heat out of the air around it. Now, what about for the winter months? If the air temperature goes down to like 5 degrees Fahrenheit, right? It's just frigid cold out there. Well, same thing. The air temperature doesn't really affect the ground temperature if you go deep enough down. So deep enough in the ground, it's still around like 50 degrees Fahrenheit. So it's going to be warmer there. And starting the house from a baseline of 50 degrees Fahrenheit, right? The antifreeze is running through the ground. It's now heating up the air as it moves through and then coming back. that's a lot easier to start from than, say, 5 degrees Fahrenheit, right? So that gets you started pumping a little bit of heat into the house, but then also it'll have something like an electric heater, like some heating coils attached to it, that also allows you to build off that. Because most people don't want to live in a house that's 50 degrees. They want it to be warmer than that, so you need some sort of additional heating mechanism on top of it. And that's why the energy savings are greater in the summer than they are in the winter, because the summer you can just use the geothermal system as the air conditioner. You don't need any additional mechanism, but during the winter you're going to need some additional heating element in order to go in there, and that takes electricity. Electric heaters are not nearly as efficient as, say, natural gas burning, but overall, year-round, it's an extremely efficient system. You save a lot of money on it. And you might notice, since there's no combustion involved, there's no production of greenhouse gases, except those involved with the drilling and construction of the system. Second form of geothermal energy is geothermal electricity production. Now, this can't go anywhere. The geothermal heating and cooling system, that can go in pretty much anyone's house, but geothermal electricity production, this has to go in areas where the Earth's crust is a little bit thin, so you're getting a lot of heat from the mantle. So areas that are kind of geologically active in that way. Convection currents in the mantle bring heat leftovers from the Earth's formation and the internal radiation towards the surface. So heat from the Earth's core, effectively, is coming up towards the Earth's surface. Underground heat warms water, and steam turns turbines and generators. So again, right, we're just using steam to turn turbines. It's just we already have these locations that generate a massive amount of heat. Why would we go to all the trouble of coming up with different ways to generate the heat if they're already hot? So we just pump water to these locations in order to generate excess steam, and then we create electricity from that. There are cons. You do need to use actually a lot of water for a system like this. So you have to pump it underground in order to get it to be heated up and then released as steam. That's water that could have been used for other types of purposes, either human social uses or your drinking water, that kind of thing, or by natural ecosystems. Another con is, pretty obviously, this cannot go just anywhere. There's only a few locations where we would be able to set up a facility like this. So here's a cross-section of the Earth to show you the process. Magma down here heats the groundwater, which we are pumping excess water down there, because if we just allowed the groundwater to be heated as steam and vent away, we would eventually lose it all. So these geothermal electricity plants need to be placed in areas where you're going to find like geysers or hot springs, things like that, places where the water is naturally being heated by the relatively thin crust and the heat from the Earth, the mantle that's able to get through. Then wells tap underground heated water or steam in order to turn turbines to generate power. And then eventually the steam is cooled, condensed, and injected back into the aquifer to maintain pressure. Typically, you also have water pumped in from exterior locations as well to maintain the amount of water going down in there, because this process can use up the water faster than natural recharge rates can resupply it. And that's pretty basically geothermal energy. I don't have any kind of long drawn out bit about it. It's got some very simple advantages and some very simple drawbacks to it. Now, there's also another way that we could talk about meeting the world's energy requirements, and it produces very little greenhouse gases, has very few drawbacks attached to it, and that's simply using energy more efficiently than we currently do. Because it turns out about 84% of all commercial energy in the US is wasted. It doesn't actually go to use any useful product or anything like that. It doesn't turn on anyone's TV or anything. Or turns on a TV that's not being watched, that kind of thing. Now, 41% of that waste is totally unavoidable. One of the basic laws of thermodynamics: for every energy transformation, you're going to lose a little bit of that high quality energy as heat. But 43% of that is just from inefficiency, from, for example, poor insulation in badly designed buildings. We spend a lot of money heating our houses, and by extension, we dedicate a lot of energy to heating our houses. And in some cases, it's necessary, but in some cases, some of those houses are just very poorly insulated. And if we went in and we added more insulation, it would dramatically reduce how much money needs to be spent, how much energy needs to be spent heating that house. Again, I'll use my house as an example. When we first moved in, went up to the attic to see what the insulation situation was, and the situation was, when they built it, they didn't believe in insulation. There was a couple of shreds of paper kind of scattered around haphazardly, but there was just mostly barren patches of ceiling everywhere. Really, there was zero insulation up there. So I went up and I put 1.5 feet of insulation in there. Got it to a really, really nice number. And subsequently later, I've also had foam injected into the walls of the house to also insulate the walls. So now my house is primo insulated, and that combined with my geothermal system, this is an extremely easy house to heat and cool. Like very, very energy efficient. And so that again not only contributes to less energy usage, but also lower costs. And like I say, many times the best environmental solution is also the best economic solution. 3 out of 4 Americans commute to work, and only about 5% use mass transit. Now, the way the United States infrastructure is designed almost requires most people to use cars, to own a car and have their own dedicated car. But we could absolutely design a better system that allows for more people to use mass transit or kind of ride-sharing systems. My pet fantasy with this is the idea of having a fleet of self-driving minibuses that many people could have, say, some sort of app or something on their phone, and they say, hey, I need a ride, and this fleet of buses could figure out the most efficient route through an AI actively updating system to get the largest number of passengers on each bus possible and still get to each destination the quickest way. So there would be kind of these constantly updating custom bus routes that would go through. And that way you would have people essentially have access to public transportation, but that public transportation could take them more places. Now that is just my idea. There's probably a dozen reasons why it wouldn't work or why it would have issues. My actual point is that as technology continues to develop, we can reimagine how to do this. We can come up with new types of public transportation. Like Lyft and Uber didn't even exist years ago, and now it's a lot of people's fundamental way of getting around. So I'm sure we can come up with some way to increase mass transit or some sort of ride-sharing system, because having every person have a single combustion engine to cart them around is possibly the least efficient system that we could possibly come up with. And also, the fewer vehicles on the road, the less traffic, so it would be a lot faster to get from place to place. Also on this slide, we have data centers. Data centers are these large facilities that contain lots and lots and lots of computer servers inside of them, and they process information, as you might expect. They use up 10% of the electrical energy from the grid, and 90% of that is just waste heat. What data centers need is temperature control. Computers operate best when they're in relatively cold conditions, so there's a lot of energy used to just keep these servers cold. I once took a tour of DuPont's data center, one of their data centers in Delaware, and it was kind of like walking around a library, except instead of all of the shelves of books, they were freestanding computer systems, right? Just large rows and rows and rows of these servers with all these wires going all over the place, and these like floor panels that could be removed to crawl under them to fix the wiring, and all this, these really massive facilities. And that's all for conventional information processing and normal data management systems. Cryptocurrency and NFTs and these kind of things, because of the way the technology is designed, requires massive amounts of computing power. I'm not going to go into all of the details of how blockchain technology functions and all the issues that are with it, but the short version is you need a massive amount of computing power in order to participate in a particular aspect of the crypto economy. The amount of power that is drawn by an incredibly small number of people, this very, very tiny percentage of the population has any interest in this stuff, is pretty similar to the amount of energy that is consumed by entire small countries. So this is referencing normal data centers, not GPU-powered crypto mining data centers, which are this on steroids. That electricity that is required for them obviously comes from what are our main electricity sources: natural gas, coal, right? Fossil fuels, that kind of thing. So they generate a lot of greenhouse gases as a result. So if we could come up with a way to make data centers more efficient, to come up with more efficient computer systems, or a way that they could be cooled without requiring all this electricity to create air conditioning systems or other cooling systems in order to cool them down, that would reduce a lot of our energy consumption just by itself, and then we wouldn't need to produce as much electricity. So this is just another way of looking at this problem. Instead of coming up with new energy sources, we can take the energy that we have and consider better ways to apply it. So here's some other ideas for efficient use of energy. Cogeneration. Let's say that you have a building, a hospital, apartment building, something like that, a school, next to some sort of power plant. It could be a short distance away, but it needs to be able to be connected by pipes. And that power plant uses steam, right, to turn turbines, which most of them do, or a lot of the different designs we talked about do. What if, instead of letting that steam escape to the atmosphere, we captured that steam and we pumped it through pipes into the walls of that apartment? We just let it kind of run up and down through the walls of that adjacent building. That building then wouldn't need to use any kind of heating system. It would be able to utilize the heat from the excess steam in order to heat itself up. So we would be able to capture what otherwise would have been waste heat for the purpose that we use heat for. Be a little bit more efficient that way. So it's one idea. I'm not sure how well it could be applied or in how many cases, but it's one idea. I've often wondered if the excess heat created by the data centers from all the computers generating all of that heat in data centers could be utilized in a similar capacity. Passive solar, right? Build buildings in such a way that they're going to be able to maximize their exposure to sunlight. So facing the sun, broad windows facing south, that's a good one. And then green roofs, which we have actually at Marple campus. We have a green roof. I'll show it to you later on this semester, depending on when this video is. It might be pretty soon. Green roofs have soil and vegetation on roofs, which increases that building's insulation. So that's one thing, is that it actually increases the efficiency of your building, but it also creates this giant platform for photosynthesis to take place. So while you have all these human societies, right, all these cities, right, that have these big footprints, and they displace all these natural habitats that otherwise may have been able to do photosynthesis, to pull carbon dioxide out of the atmosphere, by creating greener cities with green roofs and more street trees and parks and things like that, adding more natural environment into our human cities, we can actually increase the efficiency of our buildings and increase our own mental health as well, because studies have been shown just being around plants actually improves your disposition, as well as it is a carbon capture storage system. Plants pull carbon dioxide out of the atmosphere, and you can use it for a garden. You can grow vegetables out on one of these things, which are very useful. You can grow flowers on these. There's all kinds of benefits to having a green roof. Of course, in this course, we always want to talk about a couple of the policies on the books regarding any topic that we're talking about. I mentioned the fuel policy a little bit ago. Here's another Pennsylvania policy, the PA Alternative Energy Portfolio Standards. It requires that 18% of electricity sold by 2021 come from renewable alternative sources. Now, in 2015, when this slide was prepared, renewable energy accounted for only 4% of Pennsylvania's net electricity. So you might notice that we're past 2021 now. How are we doing? Well, let's see, this graph here is from 2018, and you can see that 3 years after the slide was made, I updated it. And you can see that we have nuclear is a big part of this pie slice. We have natural gas, and we have coal as two other big parts of this. And then hydro and other renewables are way down here. So pretty small, definitely not 18%. I've checked the newest graph for 2021, and the difference between that graph and this graph is that we are generating a lot more natural gas now than we were back then. Not much motion in the generation of electricity through hydroelectric or renewables. So did we fail the standards? Actually, it turns out we didn't, because this is a graph of electricity generated in Pennsylvania, and if you look at the wording, requires 18% of the electricity sold by 2021 to come from renewable and alternative sources. So this is just what energy production in Pennsylvania looks like. But if you pay your own electric bill, you might be familiar with this. Through PECO, you can purchase your electricity from a number of different suppliers. Some of them are all green suppliers. Some of them come from all wind and solar. Some of them come from a mix of different things. And you can select your suppliers. Enough people have selected to purchase their electricity solely from renewable energy suppliers that we actually have met these standards. Over 18% of the electricity sold in Pennsylvania comes from renewable sources, even though less than 18% of the electricity produced in Pennsylvania comes from renewable sources. So this is one of those situations where we're applying both economics and ecology together. Money is being sent over to renewable energy suppliers for their kilowatt hours. There might be more renewable energy suppliers in other locations, in other states, things like that. And they are actually getting some money for their electricity. So it's almost like we are virtually importing that renewable energy. And incidentally, this is what I decided on for my house rather than putting solar panels on it. I realized I wasn't going to get a lot of electricity if I put solar panels on my roof. It would not be very efficient because of all the trees around here. But I get all of my electricity from renewable energy suppliers anyway, so the effect is the same. All right, one more policy, or rather an international agreement, regarding energy production and greenhouse gas emissions, the Paris Climate Accords. This was signed in 2016 by 197 parties, which means 197 countries. The exact number of countries on Earth it really depends on who you ask, because not all countries recognize all other countries, but this is pretty close to all of the countries. And this was an agreement for each country to set their own limitations for greenhouse gas emissions. Every country said, this is what we think we can do, over this amount of time. Here's what we're going to try to commit ourselves to. And then they all agreed, hey, we're going to try our best to make this happen. This was an agreement that had no enforcement policy. There was no penalty for breach of contract. It's a symbolic agreement saying that we're all going to try. That was the spirit in which this was done. You might look at it as political theater, but you also just look at the spirit in which it's being done. Like, we're saying, hey, we're actually going to do something. And then you watch what actually happens afterward. So we started the Clean Energy Plan, the past motions in that direction. We had government subsidies supporting renewable energies. We had tax credits for any individuals that wanted to get modifications to their homes, solar panels and geothermal systems and all that kind of stuff in order to reduce overall energy consumption. And we have actually reduced the amount of CO2 that we are producing annually as a result. So we made actually a lot of motions towards reducing our carbon emissions. And many countries have announced goals to reach 100% renewable energy eventually. So it was a pretty cool agreement, right? The spirit of, hey, we're all going to try, and then many of the countries have actually been doing what they said they were going to do. Now, of course, famously, we were pulled out because it was a, quote, bad deal. How it would be considered a bad deal is unclear, as we set our own standards and there was no penalty for failure to meet those standards. Despite the fact that we were temporarily pulled out, all of the individual states and governors, they all continued to make motions or many of them, I should say all, but many of them continued to make motions towards more renewables and reduced emissions, and the United States remained on track to meet its goals regardless. And as I recall, individual states and cities were contacting the people that were managing the agreement to see if they could sign on as individual parties, like the city of New York or the state of Pennsylvania signing on, regardless of whether or not the federal government was going to support the agreement. Now, this acts as a really good segue into Unit 5, which is about air pollution and water pollution and land pollution. So we'll be talking about it a little bit again when we get into that material.